Hello, welcome everyone to this talk. My name is Terezia Slanináková, and today, here at the SISAP conference, I'd like to introduce Data-Driven Learned Metric Index and Unsupervised Approach. This is a paper that I cooperated on with my colleagues Matej Antol, Jaroslav Oľha, Vojtěch Kaňa, and Vlastislav Dohnal. We are all based in Masaryk University in Brno, the Czech Republic. Let's start with establishing some common ground in regards to indexing. The goal when searching in any type of data is to find the most similar objects to some query and to do it as quickly as possible. To speed up the search, it is crucial that we visit just a portion of the whole dataset to find similar objects, and it is the responsibility of an index to choose these relevant data partitions. To do this, traditional well-known indexes in the similarity searching domain, such as M3 on the left and mindex on the right, use distances between pivots and objects to build the index, and they equally use them to navigate the structure in the searching operation. Distances are kind of a bottleneck in the tree navigation though. They take a long time to compute, they suffer from superlinear complexity, each node needs to consider all of its children in the computation and so on. Due to these reasons, there are great research efforts trying to minimize the number of distance computations that an index needs to perform when evaluating a query. So, about a year and a half ago, we had an idea of how to address this problem, not by minimizing the number of distance computations, but by ignoring distances altogether. The inspiration came from a paper called The Case for Learned Index Structures. Here the authors worked with structured data. They took a collection of interconnected machine learning models, neural networks specifically, put them into a tree such that each model represented a node, and trained them on large collections of data to test the viability and speed of this approach as compared to the traditional structures in databases, that would be the B trees. For this training, the authors used graphical processing units, or GPUs, as the primary piece of hardware and argued for their future superiority over processors, or CPUs, because of the huge hardware improvements that GPUs are seeing in the recent years. So, inspired by this paper, we wondered if we can create an equivalent index in the similarity searching domain with unstructured data for approximate as opposed to precise search. And so we created an index and named it Learn Metric Index that works in a similar way, and this is the preliminary work for this conference paper. Let me show you how it works. So, in the beginning, there is data, by which we mean vector descriptors extracted from a digital representation of some real-world object. We feed this data into something that's labeled original index. It's one of the traditional indexes presented before, M3 or mindex. Then we collect the data divisions on every level made by this index. So basically we are noting where every object is located within the tree, and we can proceed to build the LMI. We use the descriptors as training data and the data division produced by the original index as training labels at the corresponding level. Therefore, we are talking about supervised training. To illustrate this further, the training starts from the root node, which considers the entirety of the dataset as training data, and the first level categories of objects within the original index as labels. The model is trained, and we collect its predictions. Based on these predictions, the dataset is divided into categories or groups of the objects on the following level. As you can see in the slides, the first model on the first level is then trained on a subset of the data, where the model predicted category, let's say 1, and on the subset of the labels. This process is repeated for every node in the tree until we run out of training labels for any additional levels. Then, to demonstrate how the searching works, let's zoom in on this branch in blue. Processing the query by the first node here is equivalent to collecting the discrete probability distribution of the machine learning model as a response to the query. Here, the more similar the query is to any of the child nodes, the higher the output probability is. So, in this example, we continue to the left child, which the first model identified as more similar to the query. We collect its probabilities, putting them into a priority queue, which then decides where to go next. As you can see, the next highest probability is assigned to one of the leaf nodes. After that, the most probable node is the right child of the first node, which we visit and collect its probabilities. Then we identify the next most probable node, and so on. So, using this training and approximate searching algorithm, we created a proof of concept implementation of this index. We performed 30 nearest neighbors search with various classifiers serving the role of the nodes of the tree, and we found out that the performance of LMI in terms of recall and searching speed is much better than the M3 benchmark and is more than competitive with the M-index benchmark. So, the good thing is that there are no distance computations in the searching phase of the index. Also, building as well as searching phases of LMI are able to run mostly on GPUs once we use neural networks as the underlying model. And as I mentioned, the results of this initial implementation of this idea were quite encouraging. The main limitation, however, is that we need to supply the training labels via an existing index. And this is the limitation that we decided to address within this conference paper with data-driven LMI. Okay, so what would it mean if we were to approach building of an LMI in an unsupervised fashion without the labels that the original index provides? Well, the training input will be the data and nothing but the data, and we will have to use unsupervised machine learning models to pick up the signals solely from the descriptors. This is the core difference between the previous LMI paper, where the labels helped directing the LMI training. In general, unsupervised training is more challenging, but is more typical of the real-world scenario where we have great data volumes that are not annotated, because annotation is difficult and it is expensive. So, the first model that we explored for this task was the Gaussian mixture models, or GMM for short. This is a clustering algorithm that works similarly to the well-known k-means, but instead of hard cluster assignments, it is using a soft probabilistic version of them, assuming that each data point could have been generated by any number of its Gaussian distributions with a given probability. So it can cluster the data in an unsupervised way, and we can get discrete probability out of it to be used in the searching phase. The second model is the Bayesian variation of the GMM model, which has a different way of calculating objects cluster memberships, but otherwise it works in exactly the same way. Next, we wanted to test the viability of a GPU-powered k-means implementation in a unique training combination with a supervised algorithm, logistic regression in this case. Here, the process is the following. First, we create clusters with k-means. Then we train a supervised algorithm on these cluster divisions as labels and use only this supervised algorithm in the searching phase, which makes the search probabilistic. The last model is the well-known k-means clustering algorithm. This algorithm operates with distances instead of probabilities, which is fine in index building. We are still able to get the predicted object's position within the LMI. However, in the searching phase, we cannot use probabilities anymore and we have to rely on distances. As benchmarks, we chose to use two of the best performing indexes from our previous paper. First, an M-index benchmark with a specific configuration of leaf node capacity of 2000 and 2-3 levels. Next, a learn metric index with logistic regression being the primary classifier. As for the experiment design, we performed 30 nearest neighbor approximate search on 1000 randomly selected queries. We used three distinct datasets. First, the Coffeer dataset with 1 million objects and the descriptor length of 282. Next, the Profimedia dataset with 1 million objects and the descriptor length of 4096. And finally, motion capture with the same descriptor length composed of approximately 350,000 objects. In the results, you see the mean of recall and the time of these experimental queries. We performed all of the experiments on the same machine, in the same environment and programming language, which is Python in our case. Okay, so let me first explain what you see here. This figure shows the results of Profiset dataset with the benchmark sub-LMI for the best performing supervised LMI setup together with M-index, here in purple and yellow. The rest are the data-driven LMI models. On the x-axis, we have the percentage of the dataset objects visited in the search. On the y-axis is the recall, or in other words, the percentage of how many of the 30 nearest neighbor objects were found by the approximate search. The points then represent the individual stop conditions the search was performed at. Hence, this graph shows the quality of navigation, where we want to be able to find the most similar objects for as little navigation. So we want the line to be positioned close to the top left corner. As you can see in the Profiset dataset, both of the k-means based models were able to outperform M-index and outperform or match the supervised LMI. In the Coffeer dataset, however, both of the benchmarks have a slight edge over the unsupervised LMI, most notably in the higher stop conditions. In the case of mocap, the situation is very similar to the Profiset dataset. Both of the mixture models exhibit generally worse performance and are able to outperform the baselines only in the lower stop conditions. This is the second set of graphs showing the same experiments that, as opposed to the navigation, talks about the speed of the retrieval. So datasets are the same, so is the y-axis. The only difference is the x-axis, which now represents the time taken to finish the search at a given stop condition. In cases of experiments where the higher stop conditions took more than maximum value, so 0.7 seconds in this case, we included the percentages of the higher stop condition found in this time interval drawn in the graph. This is mostly a concern of the benchmark since all of the data-driven LMIs are quite fast. So the same thing applies as in the previous type of graph. We want to look for a line that's the closest to the top left corner. As you can see, the GPU-powered k-means with logistic regression is able to find relevant objects very quickly, achieving 90% recall in under 20 milliseconds in every dataset. The distance-based k-means search also exhibits favorable recall to speed trade-off in all the datasets. Lastly, mixture models are still quite time efficient as compared to the benchmarks. So, as you can see, the classification operation that is the core of LMI searching is relatively fast as compared to the distance computations. So even in the case of Coffeer, which is the only dataset where we need to visit more objects to find the relevant ones than the benchmarks, we can effectively afford to do so because of the time efficiency of LMI. We consider these results to be encouraging. In short, the data-driven LMI based on k-means, either with or without the logistic regression component, was able to outperform M-index as well as the best model from our previous paper, considering both of the performance metrics, recall in time as well as recall in percentage of the dataset visited. So navigation with probabilities again confirmed to be viable, even in comparison to distance-based approaches. And by far the most significant benefit of unsupervised or data-driven LMI is the overall search performance measured as recall in time. Data-driven LMI managed to beat both benchmarks, M-index and supervised LMI by at least one order of magnitude. For more detailed commentary on these experiments, I would encourage you to visit our paper. So, in light of these results, let's see what the future work and the open questions are for us. We have a lot of directions for improvement of the overall quality of the LMI. Firstly, we want to be able to extend it to various data domains using not only image-based datasets, including motion capture that we used here, but also we want to be able to work with text, time series data, or very complex data such as protein structures. This will probably require the use of specialized models. Next, we want to target index scalability, so the ability to index truly large datasets and dynamicity, so support for insert and delete operations. We want to be able to improve the priority queue as well, because so far we've only used the naive approach there. And finally, we plan to take a look at optimization of building and searching costs of LMI. To conclude, in data-driven LMI, we extended the capabilities of the proof-of-concept idea of LMI introduced in our previous research paper by removing the need for a pre-existing index that was previously there in the building phase. Through experimental evaluation, we confirmed that data-driven LMI can create meaningful divisions of the data, and equally, we were able to improve the search performance in both recall and speed as set by the previous supervised LMI and by the M-index benchmarks. Furthermore, we view this work as an additional proof that the adoption of machine learning techniques in similarity searching is worth deep exploration. That would be all from me. If this topic is of interest to you, feel free to read our papers and to get in touch. Thank you for your attention.